Is that a catapult?
What's that?
That looks like a catapult.
Oh, no, that's just a large Christochrome.
Are you gonna use it today?
We used it last time, remember? Or has it been that long? Do you remember that was the one where the two balls, regardless of where you started?
I was watching it on
Oh, yeah.
the live stream.
I got you. Okay. All right. So, all right. So, oh, and I should check the buffer here. Hold on a sec. There we go. All right. So, the big news, exam 2 on Monday, a week from today. We're going to finish chapter 8 today. Exam 2 covers chapters 5 through 8. I just, yeah, I mean, we're going to hopefully finish chapter 8 today. What else did I want to say about that? Oh, you might recall that chapter 7 was a little bit smaller than some of the other ones. Oh, Jules, I need to make you co-host, don't I? Sorry about that. Got it. So you don't want to sleep on chapter 7, but to be fair, I usually do probably at least 2 questions out of chapter 6 material and 2 questions out of chapter 8 material. So I definitely focus more on chapters 6 and 8, but you have to know chapter 5 to do well at chapter 6. So if you recall, chapter 5 was Newton's law with no friction. And then we did all those things in there. So it's probably a little bit heavier on 6 and 8, but there is some stuff from 7 and some stuff from 5. Got it? So you've got practice tests this week in lab. So, and you can do that at home or you can do that here because it's practice tests. So we'll have Zoom running in lab if you want to just answer questions. If it's easier for you to work in a fire and environment at home, but you're welcome to come in as well. Any questions about the exam, or I think it's pretty self-explanatory at this point. You just got to practice, right? All right. Okay, let's get to chapter 8. In particular, last time we finished at the bottom of page 19. There were word problems. This time I want to talk about something a little bit different. Start up at page 20, okay? Get this erased. All right. So our goals today are threefold. We want to talk about determining a function for u of x from some force. We also want to figure out a force from a potential energy function. And the last thing we want to do is we're going to work with plots of u versus x. For me, it's hard to stay motivated to learn if I don't see the practicality of this. And just being straight with you, we're going to basically occasionally use this trick several times throughout the next semesters. So every time we get to a new type of conservative force, for example, in chapter 13, when we talk about universal gravitation for planetary bodies and things like that, or electricity in physics 163, we're going to have to pull out this trick. So this is basically a useful trick that we're going to use several times throughout the semesters. And these two kind of are related. In particular, it makes me think a lot about chemistry, and maybe I'll go into that later. But oftentimes, it's very easy to create a plot of potential energy versus X using modern technology. And it turns out if we have this plot, we can use that to figure out forces that act on things and figure out how things will move and do, et cetera, et cetera. So that's kind of my big motivation is we're going to use these a couple of times. And this in particular, I think is very useful in chemistry, quantum mechanics, a number of other physics techniques later on. All right. I guess I could give you the short version really quick. If you look at your equation sheet on the back, I've got this somewhere. The definition that we saw last time for the change in potential energy was minus the work. Well, I know that's minus the integral and of f sub x dx. And I just want to remind you that we're going to do Maria, that's not what I said. I never said that. Okay. Determine f sub x for u sub x. The opposite of this. Oh, sorry, I got distracted. I saw the chat. Okay, I want to point this out. Delta U is minus the work. I want to clarify here, we're doing a one-dimensional force. If you were doing 3D, we'd have like FZ, DZ, FY, DY, etc. Is everybody okay? We're just doing one-dimensional for this class. All right, you can do more dimensions in another class. All right. If you flip this, what's the opposite of an integral? The derivative. So how do you think we would get f sub x from u?
Take the derivative of work.
And what else am I going to need? What do you notice in this equation?
It's not.
The minus sign. So it's minus the derivative. Got it? Okay. Now, in particular, there's one key element in this that we can discuss while we see this. How does a derivative relate to a plot? If I have a plot of u versus x, what would be the derivative of that plot?
Rate of change.
Okay, what else? In terms of the shape,
It's slow.
slope. So notice. Nice. And you were right as well. It's just this, I wanted to think about it in terms of the slope. So check this out. If we know a force, we can use this equation to figure out the potential energy function, or vice versa. If I know the potential energy function, I could use it to figure out the force, or if I have a plot of it, I can figure out the force from minus the slope. Got it? All right. So now, if you want to skim through the derivation that we're going to do, you can look at page 20 really quick while I get the board rocking. I'm going to switch cameras here. Okay. Okay. Let's say we have some force for a spring is minus kx. All right, and it's all written there for you. We skipped a few steps here, but this is fine. If you want to do full 3D, that shows you how to do full 3D. Look, if I want to get the potential energy, remember, this is probably the part that people forget the most. Delta U. It's not U equals the integral, it's change in U. I got to remember that minus sign. And I'm going to go from x initial to x final. So remember, in this class, usually we're doing definite integrals unless told otherwise. I want to show you something here. Delta U is not U. It's U final minus U initial. And this is going to be something we have to talk about in a minute. Okay? But in this particular case, you agree the minus signs cancel. So we get the integral of just kx dx. In this case, I get a 1/2 kx squared, and I'd have to evaluate that as initial and final. right? So far, so good. I'm hoping this is pretty straightforward. We kind of did this a while back, but and here is where usually you have to make a choice. Okay. And the choice is not always obvious. In this case, what's the easiest value of X you could use? 0. Okay. So if you haven't stretched a spring anymore, right? And so let's remind ourselves, what does X mean? X is distance spring stretched. I'll get out of the way. Or compressed. Okay. If you stretch the string 0 amount, how much energy do we usually think it stores? At the initial state where X is 0, if you haven't stretched the spring, how much energy does it have in it? None. Now for this problem, it seems really obvious that we should set the initial energy to 0 and the initial value of X to 0. But in some problems, you actually want to use infinity. For example, in chapter 13 or in physics 163, think about it like this. In a different problem, let's say we have 2 planets close together, there's a lot of gravitational potential energy there. But if you put them infinitely far apart, that's when it would be 0. So in different problems, we might say X initial equals infinity and the potential energy is 0. Or in, maybe you've heard of 0 point energy. There's all kinds of times where U initial might not be 0. I could send you a video link. Well, here's the simple example. Check this out. This is a top view. Imagine we have a track, and there's a cart on this track. And we put some springs here that are under tension. The idea is there might be some energy stored in these 2 springs to hold this cart. And then as you pull it left or right, that's going to change the energy. This is a simple example where it's a conservative system. The same logic would apply, but the force equation is very different. And I could send you a handout on this later. Maybe I will if I remember. But the force would be a little bit different because you have 2 springs at an angle. So it would be a little bit more complicated. This equation would be a little bit more complicated. And when X equals 0, the potential energy is not 0. All right, is that enough on that? Just basically watch out for this. Sometimes the initial value of energy is not 0. Think about the problems. I'm not going to try and do that to you, but you have to be aware of that for later in the semester. Good enough? All right. Okay, is everybody comfortable doing this? If I gave you some function and asked you to calculate the potential energy on a test, do you think you could do that? Do this integral? Yeah?
The U is just potential energy, right? Not kinetic energy.
U is potential energy. That's a good thing. Let's remind ourselves of that. U equals potential energy. K is kinetic energy. So remember, this technique only works if the force is conservative. Remember, a conservative force means you can move it all the way around, and in any closed path, the net work done is 0. It wouldn't make sense if you could stretch this thing and then come back and have a different amount of energy. If that was the case, this force would not be conservative and it wouldn't make sense. So far, so good? All right, we'll probably do another example in a few minutes. Actually, let's do one right now. Let's try 8.22 and make sure you got this. 8.22. I'm going to go back to board 1 and erase. Take a look at 8.22. It's the next level up. What if the spring force had an extra term? Maybe if you stretch a spring far enough, it starts to act nonlinear. Or perhaps some molecules might act nonlinear. All right, so what did I say? 822. This shows you how I might mix this up on an exam. Just give you some different exponents or something, right? Before we get going here, what are the units of K? Can you tell? What are the units of K? Nope. What are the units of this? Force. Newtons, what are the units of X? So what does the units of K have to be? Newtons per meter. That's our standard spring constant. What are the units of B? Newtons per meter cubed. Why would I do that? In case we want to check the units later, right? Okay. Part A. Get U. Okay, what's the process? What do I do? Tell me. Negative the integral. We got to remember to make minus sign. That's the most common thing people forget is you're like, oh, you're in a hurry, you know to do the integral, you forget the minus sign. Let's put that in a different color here. All right. We're going to go from initial to final. That's going to give me positive kx minus bx cubed to 1/4. Yeah. All right, and so we can see this is going to be a pretty straightforward process. Hopefully you're feeling pretty comfortable with it. Notice what I say in the problem. The last line of the problem statement, what does it say?
Assume u equals 0 and x equals 0.
Yeah, exactly. So I'll try to give you a hint like that. If there's something weird where it's not 0 or whatever, I might say assume u equals 16 when x equals 0 if I was going to mix that up. But for this case, right, again, this is an upgrade to our standard spring force. All right. So in this case, oh, what did I screw up? I forgot the delta. Remember I was harping on that a minute ago? Now, in this case, it would have worked out for this special reason. And that's why I kind of got lazy there. When we know x is going to, when we know that I screwed up. Let's just leave it at that. So now, you catch it right there, right? This is the term that's set to 0. I apologize for that. And now when you stick in the 0 limit, it drops out. All right, there we go. Now look at this equation here. Let's do a little bit of thinking. Which of these terms is going to dominate for small values of x? If x is a really small number, which term is going to dominate?
Wait, why is it 1/2 of that?
Oh, I screwed up. I started talking while I was writing. The first term, right? The lower power dominates at small values of x. The bigger term dominates. So think about this. Basically, what we're seeing here is for small values of x, you get a normal spring. But at some point, if you stretch it far enough, this term kicks in and it starts modifying the equation. Does that kind of make sense? Sort of like a successive term in a Taylor series. All right. Okay, part B. Oh, this was part A. What's part B? How do we do it? No. Read carefully. What are we trying to find?
0 for u and that's all for x.
Position. Yeah, we're setting u to 0, then solve for x. And maybe that's what you said, and I just didn't hear you. So what we're going to do is we're going to say 0 equals 1/2 kx squared minus 1/4 bx to the 4th. Do you agree one answer is x equals 0? So that's one answer. Let's make sure we get that answer, right? We should get another answer as well. But so when I do this, it's important to notice that, right? Maybe I'll write it like this, just because this foreshadows the next chapter. I'm going to redo this, but check this out. I know this seems like old school, 8th grade type stuff, but watch this. Let's factor out that x squared. Just trust me on this. I guess I could factor out a 1/2. Do you agree? Make sure I didn't screw that up. The reason I mention this is when you factor it like this, we see the two solutions easier. You know what I'm saying? So sometimes this old school factoring technique is actually useful, and we're going to use this in the next chapter. And it turns out sometimes the first answer, the one everybody ignores, is actually the one you're looking for. And more on that next chapter. All right, so from here, what do we get? Anybody solve it yet? Let's see, 2k over b equals x squared, is that right? So what's the position? Yeah, I was looking for the plus minus, just seeing if you would remember. In this case, you could stretch the spring to the right or to the left. So in this problem, it's probably useful to think about. Basically, anytime you got to take a square root, think about the plus minus. Here, stretching something to the right versus left. Sure, there's two possible positions. All right. So far, so good? Let's see here. Let's do part C. Let me get on the right board. It's weird. After spring break, I'm a little off on my remote work here. I'm just a little loopy. Okay, part C. It's important that you understand what this question is asking. What is it asking? What are we trying to figure out? No, it's part C. Determine equilibrium positions.
Oh, my mistake. No.
Which one? Oh, yeah. Part C, determine the equilibrium positions. What does that mean? In particular, you're supposed to know something about this word. What does this mean?
Equals to,
What is it?
equals to, or like balance.
Oh, okay. What balances when we're in equilibrium?
Both terms.
Okay, yeah, force. So that's what we're supposed to be thinking about. The net force is 0, or in this case, the two terms balance. Does that make sense? Just because if this is on a test, I don't want you guys to not know what that word means. Basically, it's just a fancy way of me saying, when does the force equal 0? Got it? All right, let's keep rocking. So in this case, what was our force?
Negative kx plus bx to the cube.
All right. What technique should we probably use just to get all of the correct answers? Factoring in this case. So notice there's a solution, x equals 0, or so then what do we get? X equals plus or minus the square root of k over b, if I didn't screw it up in my head. Got it?
Yeah.
How could we check that answer? Our unit check, right? What are the units of K? I think they were newtons per meter. And then B was. And then whenever you get multi-fractions, don't overthink it. Multiply by the reciprocal. Kind of a nice way to get started after break, right? Wait, it's meters after you take the square root. That's good. So far, so good? All right. And then it says, okay, there are some numbers after class. You could dump this into Excel and plot it. Look carefully. It says plot, I want you to read that last part. It says plot f sub x versus x and u of x versus x for these values between -8 and +8. What's going to trip you up if you weren't paying attention there?
The universe.
What's that? It's
Parts negative.
no, there's something else I want you to notice right now. Read that last line. After class, plot this crap between -8 and 8.
Centimeters.
How am I going to mess with you on test day? Units. You see what I'm saying? We're going to see this all day long. Okay, this is how I get the units in there. Every plot we're going to look at is going to have messed up units to make sure you pay attention to the units all the frickin' time. Got it?
We have to convert our K and B.
You could either convert K and B, or I would think it's easier to just go to -0.08, right? Because it's easier to convert to X into meters, probably. Got what I'm saying? Always watch for your units. All right. Okay. I think that's pretty good on that one. If you're curious, you could look at 8.23. The goal of 8.23 was to not only discuss 1968 era zombie versus 2000 era zombie, but also to talk about conservative forces. So if you've forgotten, let's look at the definition down at the bottom. The work done is path independent, meaning you could take any path and the net work done on a closed path is 0. So for example, if you had a situation like 8.23, you could have the zombie go up the ramp and down the ramp, or down the ramp and up the ramp. And you can make sure the work done is 0 if they start and end at the same spot. If that's not true, right, it's not a conservative force. So the tension in the string, for example, is not going to be conservative, and the friction is not going to be conservative. All right. Let's go to the next page. 22. And maybe for this one. Oh, yeah. Yeah, let's go to page 22. I'm going to erase the board. You look at it. I think the most full the class has been in weeks. Pretty cool. By the way, sorry about the snafu on the building on Friday before spring break. I got it figured out. They're supposed to have it unlocked. It will be now, but what a nightmare. So I'll try to grade you nice because it was my screw up. Even though the building, we have classes in the building on Friday, it's supposed to be open. Sorry.
Are we getting our laps back today?
No, because I didn't get some of them until today. So I'm like, oh, but you'll probably everybody be getting an 8 or a 9 or higher. I'll just say it like that. How about that? All right. Okay, we've got these two ways, I discussed them earlier. If we're trying to understand force from potential energy, whoops. You can either take minus the derivative or think of that as minus the slope. And to be honest, more often it comes up as minus the slope on a test day, okay? That doesn't mean you shouldn't know the other one. It's written on your equation sheet, but basically I expect you to understand minus the derivative, minus the slope, interchangeable. Okay. So let's just say we have some crazy looking plot here. Doesn't have to look exactly the same as that one. Kind of looks similar. All right. And maybe I'll make this keep going this way. So this, to be clear, this is u of x, and on this side is x. We always want to be thinking about the units, so I'm going to write units here with an exclamation point. Always check the units. And maybe so that this isn't confusing with multiple sets of parentheses, we'll understand that when I say u of x and u, I mean kind of the same thing. We should always check the units on any graph. That's important. And we see here, this is supposed to be perfectly flat. What do you notice about the slope right here? Right here.
It's not T, it's 0.
It's 0. What's the force? Where else is the slope equal to 0? Just tell me when.
There. There.
Right?
At the peaks.
So here, slope equals 0. Well, slop. All right. At those points, the force is equal to 0, right? Those are called equilibrium points. Okay? Is everybody okay with that? Remember, force equals 0 is the same thing for us as saying equilibrium. Now, to be clear here, you may be saying, wait, what if there's more than one force, etc.? Let's assume this plot takes into account all the forces. Or, as I typically say on your exam, let's assume there's only one force acting on the particle, and this represents it. Now, you might be saying, wait, we're drawing U. Remember that U and F are interrelated. If I draw U versus X, I'm basically drawing F versus X if you take the slope at any point, right? Right here. Is F sub X positive or negative? How do you know? Yes, because the slope is negative, and that's the thing you got to think about. Now, I know it's going to sound a little bit strange. It actually looks a lot like. Oops, wrong way. Oops. I guess we're right on your head. Sorry about that. Yeah, just for a second. Is that close enough? She's not in the way anymore. All right. Think about it like this. When I let go of this, you can see this ball rolling back and forth, right? Notice on the downslope here, there's a force this way. And on this side, there's a downslope this way, there's a force that way. You can literally think about a ball rolling on a track similar to the potential energy function, with one important exception. This ball is moving not only left, right, and up and down. Do you agree? If you imagine just the shadow of the ball, like imagine if I put a light up here and shine this down, the shadow of the ball would be moving only right and left. Agreed? That's how I want you to think about this analogy. A ball rolling on a track, and actually the shadow of a ball rolling on the track, represents the motion of a particle. Let me go back to this board. This is really cool. All right, think about it. Now, we're not going to be talking about a ball on a track. We're talking about the shadow of a ball on the track. So let me draw the shadow here. We'll call this the track ball shadow. I don't know. Right here, the shadow would move this way. Then it would slow down. Then it would slow. Okay. Then it would speed up. And it would go back and forth. Wait, how far would the ball go? If I release it from here, how far would it go? It looks like it would just barely make it to there. Would it make it up to the top? No. So it would turn around right here. Isn't that cool? Now think about this. If you release the ball from rest here, we'd expect it to roll down, slow down, then speed up, then slow down, then reverse, then go back and forth. What's amazing about this is if you can understand a plot of potential energy versus X, you can actually understand the motion of particles. And this is useful in chemistry or, like I said, quantum mechanics, et cetera, et cetera, et cetera. So this idea of thinking about the ball's shadow will help us analyze whether the force is to the right or to the left. You have a negative slope, F sub X is positive, force to the right, it speeds up. All right, and then similarly right here, the force would be because the slope, got that? And we're going to use this again in physics 163, right, Jules? A lot. Okay, or at least for one more chapter. So we use this trick a couple of times. Good? On pretty much every test, I ask a question. And I ask you, which way is the force on it? And I include an answer that says like up, down, left, right. Remind me here, this object is F sub X. The force is to the right or to the left. Just because the ball would roll up and down doesn't mean the force is up and down. You got that? I'm trying to emphasize this because I'm going to ask it and hope you don't screw it up. That's why I'm trying to do this stupid shadow bit, right? The force on the shadow, you can imagine, is only left or right. Not up and down, even though it looks like a ball would roll up and down. Good? Where's the ball going to spend the most time as it rolls back and forth? At the edges?
No, the place where the force is
Well, let me talk about here. Do you think the
Okay.
you think the ball is going to spend a lot of time at this spot?
At
No.
the maximum?
At the maximum, right? Think about it. As you go down, what happens to your potential energy? Does your potential energy go up or down as you go this way? It goes down. So what happens to your kinetic energy? So, right, as you go down on the plot, U decreases, so kinetic energy increases, right? Hidden inside of this is this equation. Think about it. If you start at a particular value of U and you have a certain amount of kinetic energy, then you go to a lower value of U, right? If this goes down, this has to go up. Conversely, if this goes up, this is going to have to go down. Agreed? Conservation of energy. That's what this is all about. So you can see this thing, it's going to spend the least amount of time where?
At the minimum?
At the minima, a little bit, well, it'll be kind of low amount of time, but we'll spend more time here than down here and spend a lot of time up here, right? Where it's moving slowly. But just for fun, imagine you're an electrical engineer and you take some semiconductor substrate and you put different layers of semiconductors together. You get these plots that look like potential energy versus X. And you can describe how the electronics will behave. You can say, oh, well, if I have an electron up here moving back and forth, It's gonna spend more time in here, and maybe that helps me make a better VCSEL, better laser. Anyway, so that's foreshadowing. There's actual use to this stuff, which I think is super cool, because I kind of have an electrical engineering bent, just a tiny bit. Good with that? You're not really gonna get this till we do some problems, agreed? Let's see if there's anything else in here I forgot. I'm going through the bullet points on page 22. Watch out for the minus sign. Everybody forgets it. When the slope is 0, you're in equilibrium. Oh, equilibrium are stable, unstable, or neutral. Okay, let's look at it. Think about the ball released right here, right? It's going to rock back and forth, and it's going to oscillate about this equilibrium point. That makes this stable. Okay, so the idea, if you're at a local minima, it's a stable equilibrium point. Okay, now if you're up here, what if you're displaced slightly left or right? You're going to take off, right? This is unstable. Okay, so any small displacement from the perfect equilibrium point, you're going to go flying away, agreed? If a ball was slightly on the other side. So that's why this is called unstable. Now up here, if you put the ball or the marble, if it's at rest, it's going to stay at rest. If it's moving to the right, it's going to keep moving right, but it's not going to speed up. If it's moving left, it's going to stay at that speed. So that's why this is called neutral equilibrium. For the neutral equilibrium points, basically your speed remains unchanged and you just keep going in the same direction you're going. So there's stable, unstable, and neutral equilibrium points. Sometimes on a test, I'll say, label all the neutral equilibrium points or label all the stable equilibrium points. You guys feel like you could do that? Basically, you got to review this, do a couple practice problems, and we should do that. Let's see what else we got in here. Think about how the marble would roll, and really, it's just the shadow of the marble. Oh, units. Look at these units. Units are often nanometers and millieV. Now, I don't think I've mentioned this before. 1 EV, that's 1 electron volt. So you know me, I like electricity. I'm just telling you about electrical engineering a little bit. I want you to think about EVs as a tiny amount of joules. It turns out in electronics, EVs and millieVs are common units. And obviously, electron volt, we're going to use that a lot in physics 163, but okay. So just know that this is a unit. And if I put that on the test, I believe, is that listed in your equation sheet? Yes, it is. That's on your equation sheet. So you don't have to memorize that. Just know that that's on the equation sheet. You got it? When I was in school, one of the things I would always screw up is right here. So just remember this. I would sometimes forget the minus sign. Just remember 1 EV equals a tiny amount of joules. Okay, and EV is a tiny, tiny, tiny. Electrons are tiny, EVs are tiny. Okay. And then finally, we mentioned this already, but again, what is the main point of this? Why are we learning this? This has uses in the real world. Some of the applications are listed. Let's try 8.24 now. 8.24. Okay. And while you're getting started reading that, oops. All right. Border race. Okay, we've got this weird potential energy function. Number is this 8.24. Practice. So believe it or not, this is not just some stupid function I'm making up out of nowhere. And I've got a simulation that's going to help us understand the meaning. So right now it's going to feel a little bit like math, but just trust me, I'm going to show you a simulation at the end to try and help make some sense out of all these symbols and give it some meaning. That said, I want to practice the math techniques too. All right. So this models the interaction between two atoms. We've got polyrepulsion and an attractive van der Waals force. All right. Okay, so now let's see, where do we want to go with this? What are the units? Help me out. What are the units of U? Joules. Now, these two terms, this is a difficult problem, but if you're going to add two things, what has to be true about them? In terms of their units, if you're going to add two things, what has to be true? So that says the units of sigma over x to the 12 have to equal the units of sigma over x to the 6th. What does that say the units have to be? Well, can I divide both sides by a sigma over x to the 6th? What's left on this side? No units. 1 means no units. Agreed? Well,
Wouldn't that just be 2 on the left?
what's that?
If you divide it by to the 6th.
Oh, no, it'd be. Oops. Oops. Do you see it now? Yeah. Got it? Okay. And let's just finish it, right? Well, what are the units of x? We could rearrange this now. Whoops, I guess it doesn't matter whether you have it inside or out. Do you agree I could take the 6th root of both sides? What are the units of sigma? Meters. What are the units of epsilon? This whole thing is no units. So what has to be the units of epsilon? Joules. So the idea here is this constant relates to the energy associated with your two atoms, and this constant must relate to the size of them. Okay. So I'm just going to summarize this up here. The units of sigma are meters. The units of epsilon, gee, that's a convenient E-looking symbol. So it has units of joules. So far, so good? Any questions before I erase this? I suppose I could keep working on the other board, but I just like having this. All right. Tricky unit analysis. You're good, or did you need something? Or?
No, my foot was about to cramp.
Oh, I got you. Yeah, you go. We'll probably take a break right after this problem, right? So, but yeah, if you got to get up and do whatever, do whatever. Yeah. All right. So now, I think I can erase all this too. Sorry. All right, what's the next part? So we're gonna ignore the units for this particular problem, but all the other ones, I'll bring it in. Determine the force. How do I get the force? Remind me. Negative what?
Derivative. Sorry.
Yeah, here's a trick. Look at this. What are the units of U? Joules. What's a joule? Newton times a meter. What are the units of a derivative with respect to x? The x is in the basement, so it's,
1/.
what are the units of this? Do you agree the units check? Don't forget, you could do units on derivatives and integrals. Think about this. What are the units of what are the units of dx? Meters. What are the units of force? What are the units of work? You can do units on derivatives and integrals too. Is everybody cool with that? Just helping you check your math. So if you forget that, that's one way you could do it. What's the other way? During the test? Read the equation sheet where it's listed. You know what I'm saying? So believe it or not, people forget to check it on this problem in particular because you're so used to doing it. Don't forget to check the equation sheet and make sure you didn't flip a minus sign or something. That's why it's there. Okay? Or flip a dx for a, okay. Good enough on that? You guys got this? I'll race you. Go. And then Jules, if you're wanting to walk around, you could help them. Dom, if you want to too. Maybe I'll do that as well. It's been a while since I've done that. Usually people make one or two mistakes in this one, so let's see. I'll give you a second to get started. Okay. Got it already? Or
Take it.
Okay, okay. Thoughts on it?
Yes.
Maybe some-
Epsilon a variable or constant.
Epsilon and sigma are both constants. Yeah. Did I forget to say that?
That makes it really easy.
Yeah, epsilon and sigma are constant. Oh, yeah, somewhere in the problem statement it says that. I don't know. It's. Yeah, there we go. Huh. That's all. Could you check his and see? First one. Hint, consider rewriting x to a negative power. We don't screw it up. We're doing derivative this time. Yeah. Derivative. Yeah. So notice this is where you're gonna get on test day. This shows up. Before you do the integral or the. Yeah. I know, because I've done it many times. I'm like, whoops. Yeah, you don't want to do the math and then you don't. Yeah. Double check that. Yeah, exactly. So now it's like the constants pop right out. Epsilon's a constant, sigma's a constant. Here, let me check this. I didn't say it, but it's written right there. Sigma and epsilon are constant. So those just pop out. Jules, did he have it or did he have something flipped?
I can't tell right now.
Oh, okay. When you take a derivative, does the power become more negative or more positive? Yeah, so he had 11. Yeah. See what you, yeah. That might help too, if you need to see it. So I put a couple of warm-up steps on the board just to see where it's going, if that helps you get there. If you want, you can go ahead and see the rest of the page. I think, remember, you can check the answer if you're already done on the solutions, or you can. Yeah, sorry about that. And if you're already done, yeah, some people, right, we just gotta roll at different rates on our derivatives, so.
Is that a derivative?
I know, so it's a little bit.
A little bit. Spend all week.
Exactly.
Okay.
That's all I did on spring break, was work on
Yeah,
that
so,
joke.
yeah, then, yeah, 6.
Oh, yeah.
6.
Yeah, so that's gonna screw everything up, fix it up. You got it. That's why we're doing this. What's that? The 4 and the sigma doesn't change. Where happened to your sigmas? But it's multiplying by everything else. You could check the units, it doesn't make sense. 'Cause
This, you don't write this.
This is.
This, you will take the derivative of what's inside.
So sigma has to be equal to, it factors out, just because the derivative comes from 0, it becomes something else. Right, like 3x, you don't just get. Yeah, so go ahead and check on that if you want.
Let's see.
I'm gonna go ahead and keep working up here, you guys just keep working out there.
This goes in front. It's the derivative of. Yes. So in my class, I marked that wrong. That's not how you write the derivative. Would you put it in that class? It's not a product. It's not 3 times 8 is 8 times 3. This is like f of x. X times f. This is the function you're doing. This function is the derivative. Okay, so. So. Go off here, 1 over x to the 12.
So that's wrong. Yeah.
Tricky problem, isn't it? It looks deceptive, but it's actually got some tricky stuff in there. Is that what you got? You getting there?
No, I just kind of did an extra step at that was.
Okay, okay. What could you do with that answer? Check it.
He's getting confused because the X in the.
Yeah, if you get done, check the units. Make sure you can check the units and think it through. So that was the whole point of understanding the units of sigma and epsilon. See, you can do a unit check on your final answer. Make sure it's valid.
Yeah.
All that's supposed to equal 4. What do you think? You
I
getting there?
just, I always forget to
Yeah,
just like
take a look
split
at
it
that.
up.
Is that what you got? You see back there?
Sorry.
Think you got it. Yeah, question? What's that? Yeah, absolutely. I had got it at 7. It would make sense to pull up. Yeah, because you factor out the epsilon too, right? It's stinky when you get negative powers, isn't it? So notice here, I can factor out a 6. We should get 24 epsilon times the quantity 2 sigma to the 12th over x to the 13th minus 6. Wait, I already factored out the 6. Minus sigma to the 6th over x to the 7th. That's what I got. I hope I didn't screw it up. What's one way I could check this? Check the units. What were the units of epsilon? Joules. What's another name for a joule? Newton meter. Okay, so now I have a Newton meter times, in the first term, what are the units of sigma? Meters. So I got meters to the 12th over meters to the 13th. Minus meters to the 6th over meters to the 7th. Do you agree the units are newtons, as we expect, for a force? We're looking good. So far, so good? Good practice. Part C. Part C says determine the equilibrium position. Equilibrium position. What does that mean? Set the force to 0. Go. I'll race you. And so in this case, that's why it's handy to factor out that 24. There's just less crap to deal with. The constant can't equal 0, so that means the only way it's possible is if this equals that. And again, this is actually a model that's useful to human beings. That's what's crazy about this. You look at this stuff, it looks like nonsense. Okay. The 6th root of 2 times sigma is equal to x. And I think I did the math on that. What did I find? 1.12 or something? I gotta punch it in on a calculator. Two raised to the 1^6. 1.122. I think the decimal is more enlightening than the 6th root of 2. Does anybody here have that memorized? Probably not. So far, so good. Did that make sense, or did I go too fast there? Or? Basically, I set the force. Basically, this was the important part. If we want to find equilibrium, you're supposed to know set F to 0 and solve for X. Got it? Okay. When we do that, we get this answer. So now, I deliberately did not label these plots. I don't like to do that usually, but for this one, I wanted you to look at the plots and tell me which one's U and which one's F. I don't normally do that because it makes me kind of sick to see a plot without units, etc. But which one of these is going to be force and which one of these is going to be U? Hint. What does the equilibrium position mean? When X equals this value, what goes to 0? The force. Look at the two plots.
Oh, the bottom one.
The bottom one has to be force. The force goes to 0. See where it hits at about 1.122? So the bottom, now you can label the axes on there. The bottom one should be F versus X. So you have two plots here. This is U versus X. This is F versus X. I'm going to remind you of something that we did earlier in this method. X versus time and V versus time. When we're going this way, what did we do? To get from X to V, we,
Take the derivative.
with respect to
T.
T, if I'm going this way, you integrate. Now, that's what you're already ahead of me. There's a subtle difference between XV and UF. So on the UF, what do we have to do? Minus the derivative. That's what's different here. With respect to X. And if I'm going this way, minus the integral with respect to X. Got it? So it's similar, but that minus sign is diabolical because it flips all of your reasoning upside down. We see again, I'm big on understanding graphs, right? Because I don't know what you're going to do in your life, but odds are, if you're going to be an engineer or doing some sort of technical work, you're going to have to understand graphs and their relationships. So I could care less about which particular graphs we're studying, but there's going to be a graphing question on your test, and it's going to be related to something like this. Got it? Because right? All right. Enough said. Kind of like chapter 2. I wanted graph on every test, All right. I know it's getting close to break time. Let's play the video game really quick. All right. You guys, you can chill out for a second. Give me a second. Are you starting to get a little bit of a hang of this or not? You need a little bit more practice, obviously. Come on. Okay, so hopefully you're on Zoom. Can you see that as well on Zoom? Good, thanks. All right, I know this seems crazy. I'm going to go custom just because I'm such a custom guy. The idea here is this I think will help you get a visual on what this is supposed to mean. And maybe I'll pick different atoms that are. Whoa. Trying to find two that really stand out on the screen really well, but I'm going to go with argon versus argon. Can you see that at all? All right. So again, sigma, if you look at it here, that's this distance right here. That's this distance right here, the distance between the atom centers. So that's what sigma means in this calculation. Epsilon is this parameter that relates to its potential energy, right? So that had, now we know a little bit about how these things work. Let me clear all these drawings. If I pull this thing a little bit and let go of it, what should happen? Think, talk to your neighbor. I'm going to let go of this in just a second. What should happen? What direction is the force on it? Is that kind of what you expected? I'm going slow motion now, right? Where does the particle spend the least amount of time? Right at the bottom. What's true about the force at the bottom? 0. How do you know? Slope is 0. You guys did pretty well on that. So the combination of being able to do the math and understanding the plots is super, super strong, right? You can learn a lot from this stuff. So now let's go to this custom, and I apologize here. Oh, let's show the forces too. We can look at the total force, right? So in this case, right at the equilibrium, you see the force goes to 0. And let's go custom just so I can make this bigger and make it easier to see. All right, let's go there. So now what I'll do, and actually we could do this instead. We could see the two terms. And so we could see that at some point, when the atoms get really far apart, there's the attractive van der Waals force that causes them to come together. If they get too close together, your electrons don't want to be right next to each other. You have electron on electron, negative charges repel negative charges, and they spread apart. What if I go way out here? What do you know about the equilibrium out here, approximately? It's neutral, right? So it's not exactly neutral. Do you agree it's ever so slightly going, they're going to gradually come together here, but it's approximately a neutral equilibrium. So if I release it from rest out there, it's going to stay at rest for a long amount of time. Now you can see it starting to creep. What about the other case? What's going to happen if I jam these together like this? Whoops. Right there. What's going to happen if I release this thing from rest? It's going to fly away and never come back. The atom breaks apart. All right, what do you think? Any questions about this? I think I gave you some comments. So basically 8.25 was basically what we just discussed. We talked about it on a conceptual level, and that's fine. And notice at the bottom, I did finally include the units. Oftentimes, epsilon has units of millieV or MeV, and the X units are usually nanometers. So I think we should take a break, come back, and just do practice problems like the ones on the next pages and just go nuts. You got it? All right, I'm calling that for a break. Good job, everybody. That was intense.
How's your break there, Seth?
Too short. Yours?
What's yours?
I like that octopus.
Thank you.
What's the, I can't see with the sticker on
Oh,
it.
it's from the San Francisco Aquarium.
Oh, that's cool.
Yeah, my family went there like 2 months ago, and I got this one.
That's cool. I like it. I like the purple. I like all that. That's a cool shirt.
I was gonna get like a black kind of like bomber jacket, but it was
Uh-huh.
too expensive, and this one was like looked a lot cooler.
It's funny. I got my kids a stuffed animal octopus, and they were just like not into it.
Really?
Yeah, I like. Yeah.
How old are your kids?
almost 10 or 11 or something. I'm not good with ages. They were born in 2012, so what is that?
That's like 10 years.
Yeah, so there you go.
So that's crazy to say 2012 was like 10 years ago.
I know, right? It's hard to believe I've been here since '05. Dom, when did you start at Hancock? 2000? 02?
So that's 20 years.
Yeah. That's crazy, huh? I don't know.
I don't know whether they didn't like the octopus.
What's
On my-
that?
I don't know whether they didn't like the octopus. On my job, we have like some stuffed animals that are for like charity and stuff.
Yeah, yeah.
And I just bought like a big ass bunny for myself.
You guys, how does that, well, do they have to be brand new stuffed animals? Or could you take used and clean them?
Well, no, like Kohl's just provides them.
Oh, yeah, yeah, because I was gonna say, I don't think you're legally allowed to give out used stuffed animals. or
No,
something, Right?
it's like brand new one.
Yeah, it's too bad, because this one's basically brand new, and the kids never play with it. It's a really cool one, but maybe I'll just put a bolt inside and shoot the octopus down instead of shooting the duck. All right, all right.
Have you ever had octopus?
Oh, yeah, yeah, I love octopus, which is sad, because it's like they've got really good brains, but man, they're tasty too.
What about duck?
Yeah, I eat duck. Not a
So
big
that's how you
fan.
got smart.
What's that?
So that's how you got smart. You know,
That's
the
right, I just absorbed their brain. Yeah. One of my favorite octopus salads, right? You get octopus salad and slice it super thin and just olive oil with salt and oh, so good.
I'm not a big fan of seafood.
No.
But I grew up in like a Bay Area,
Uh-huh,
Mexico.
I got you. And you didn't like seafood? Or you had to eat it all the time?
I'm still kind of getting into it. And I actually wanted to be a marine biologist before I wanted
Oh,
to study
yeah.
this.
Yeah, I grew up in the Midwest, right? So there was never really good seafood. So although we could get good walleye, I don't know if you know that fish. That's a freshwater fish. It's pretty good. So I'd eat walleye as a kid. But yeah, so then when you come out here and get fresh seafood, it's like, oh my gosh. It's probably not good for me, man. Probably should eat vegetarian more, but I try to eat a couple times, you know. But not to eat, try not to eat meat at every meal every day, but
But you need your protein.
yeah, yeah. I like tofu too. Yeah. Are you a cook or not? You cook?
Some
Like
Mexican
home
stuff.
cook? Yeah. You got cast iron? You
No,
use
we use stainless steel.
big cast iron fan. but-
What's your favorite like seafood? Octopus?
You know, tuna sushi. is
Really?
Good. I like tuna sushi. But like I said, I do like octopus. I like fried fish too. I like fish fry. Just unlimited fried fish. When I was a kid once, I ate 10 fillets. I was just like going crazy. Then I was like laying around groaning, but still happy. Fried fish sticks. You? You said you don't.
No. Well, like the only thing I eat is like like fried fish. My family likes tilapia.
Yeah, yeah, yeah.
So that's basically what I
That's a good one. Or taco or something, burrito. Like that. I eat catfish too. I mean, I'll eat anything. Except mayonnaise. Not a big mayonnaise fan. Or
You
sour
like-
cream. I don't like mayonnaise or sour cream.
really.
Yeah.
What's your favorite condiment?
What's that?
What's your favorite condiment?
Oh, I don't know.
Okay,
Cheese?
Does that count?
Yes, of course. It also counts as full meat.
Yeah. Sometimes I put steak on my steak.
Yeah, for Dr. Gottlieb's labs, we're gonna start quantum levels of like energy.
Yeah, yeah.
And he was like, "Oh, it's one of my favorite topics," and I just like TSM, it was because it was all physics.
Yeah, it is, yeah. It's, yeah, if you want, we can talk about it in office hours right after, and give you like a super brief version of it. Because you might even understand it after this. I can show you some models of how you get to it. It turns out it just naturally, yeah, it's just a weird, sort of like the waves on a string are quantized. There's certain frequencies that a string can produce. Same thing with energy levels. Yeah, we can talk about that. It takes a while to set it up. About 25 minutes to talk about it.
Okay.
Maybe 20. Wait till physics 162.
I think.
When did we go on break? Do we still have a couple minutes or is it about time? Does anybody know? We'll wait like one more minute just in case. All right, so we're back into it here. I put up a couple of problems here. 8.26, 27, and 28 are all good. 29, 32, and 33 are sort of like the problems we did last time. We've actually finished this chapter. All we need to do now is practice as much as possible. If you don't practice at this point, you're going to be terrible. So we've got to do some practice. I'm throwing these problems up here. I say we spend the next hour just practicing like crazy. And since we've been doing these plots, I would do at least one of these. And then if you're bad at it, maybe do two of them. And then if you want to practice some more word problems. So let's try 8.26. And then if you finish, right, just do one of these extra problems here. And I was thinking I'd just start circling and helping you one-on-one, right? That way we're doing this. Is that okay? Right? And if I see something that you guys are all struggling with, we'll do it up on the board together. All right, so let's do it.
do some of those problems. Start with 826, and then after that, choose your poison. Okay? And so I guess if you're in a future semester watching this on Zoom, this may be like just boring for the rest of the time. So you may want to just start doing the problems with the workbook. All right. I'm gonna just start circling, and yeah, Jules, you can give him a second to get rid of one if you want. Equilibrium means force equals 0.
So it also means dissolution.
That's right.
It's not something strong.
Yeah. Yeah, so, good. What's up, homie? Yeah. Sort of like right here, right? At this point, there's no force. So it's not that you don't have velocity, it's just that your velocity is not changing, your acceleration is zero, right? So I really like this marble analogy. Enough on that? Can you hear that slipping too? That's the sign that it's slipping. Oh, that's chapter 10. So rolling with slipping. It's also not on the 10th. It's on that's later. Tom, you do roll with slipping, don't you? Yeah. All right, so what's this? What you think? Got some ideas? Oh, yeah. Sorry. If you need a laptop. Sorry about that. Feel free to use the solution. Like, try it yourself, but if you get stuck and you're waiting for me, use the solution for sure. And if you want to move to one of the tables with the big screens, you can do that too. Yep. Yeah, that big meeting tomorrow, right now.
Stuff up there.
Yeah, I'm giving them lists of videos and everything, so I gotta talk to Matt before I gotta haul up. Yeah. I have to pull the seats out of my. Yeah, so Thursday, probably, I can probably. Do it for about- So, yeah. Yeah. So there's just you and me. So we can park it. Right? So, yeah, that's. I don't know where we park or whatever. We'll talk about that.
Yeah, it's something to do with
I'm assuming I'll drive. And then what is it, 8:30? So we need to leave probably at 7:30.
I don't have a patient that's here.
So get there a little early. I don't know when I can load that stuff in. So I gotta. Oh, sorry. Oh, yeah, plot is showing. Where's the equilibrium? What's possible is that the slope right there, which one stay in section? Good. Don't forget the plot shown right above there. You can read the equilibrium off the plot and then check your answers with your derivative. You know what I'm saying? Did that make any sense? I hope that did. You've got the plot to get the equilibrium points, but you can also use derivatives, right? Take the derivative, negative the derivative, and set it to 0. All right. Okay.
You want a laptop or you got what you got? Here. You need a laptop or you got your phone for checking the solutions?
Okay, yeah. Don't forget to check the solutions after each part.
You think you got an idea?
Okay. Right?
got it, got it. So you can do it either way, but you check, it. So now you know what kind of number should be out. Yeah, just imagine the model rocket, the bottom, it's stable. Model will go away, it's stable. Model will go, speed is kind of like this, right? So this is stable. This is neutral. And then, I guess we don't really have any. I guess if you could imagine this just going over here and here, right? This would be an unstable. If you tilt it just a little bit. Flip it upside down. That's a good idea. What's that? Yeah, the concavity. You do much with the Weaver sex plots, don't? Yeah, that's true. Zero flash. So under load, what's the energy? Get there? Okay. You? Okay. What do you think? So far, so good?
Number sheets.
Oh, yeah. So yeah, just plug, no, just. you
Oh, I
have-
plug it into the.
Plug it into your equation, right?
Oh.
Yeah, you could do that. That's a lot harder. That's a lot. Now, if you wanted to, you could get negative the slope at each point,
Mhm.
but that's gonna be very time consuming. True. That's why we take the derivative.
Are you?
Yeah, exactly. So then it's just plug it, that way you got some dots. Let's see if you get the same plot I did.
Yeah.
All right. Basically, yeah, okay. You're good. What do you think? Getting it done? Okay. Sounds sense? Okay, so about plus or minus 1.6, does that match up with the graph pretty well? No. All right, I like it, I like it. It's all good. It's all fine. Thank you. You good? Oh, okay, so you already did that. That's awesome. What do you feel on this stuff? Do you kind of like energy or you get the hang of it or not? Yeah, that's basically your working problem. All right. Oh, wait a minute.
you, the graph says it's positive. Which way is it? Metrics.
Top, which way is AC?
These calculations. Force function is probably.
Oh, now you want me to. Which way is AC? Oh. Accelerate upwards. You feel the head down, right? So the bottom is like, oh, you're at the top. Right, so your normal force. You're not gonna be happy with it. Think about it, you have to be accelerating upwards, the upwards force has to be bigger, so you can't. Does that make sense? The normal force here is not. the same as that. Yeah. Cool. We don't know. But you could figure out AC and figure it out. See what I'm saying? AC is going to be square root of R. How do you get the V? Right. We know this. Can you figure out the velocity here, using energy equations? Now we know the height, right? We know the height. Now we know the potential energy. Use that to figure out the V. So you get it. So it's like doing the problem two ways. Here we use the force to get the height. Now we can use the height to get the force. Does that make sense? It's like a classic example of difficulty. Or you got it there. Can't you see? Can't you see? Okay, go ahead. So far, you. Yeah, that makes sense for the picture, right? Wait. So you'll get that thing. Okay, which ones are staying up? Okay, cool. Does that make sense for the picture? Yes. Oh, you got it right there. So you got all three. Nice. Good job, dude. All right. What do you think? Yeah. That's cool. All right. So we'll let you keep going. Here on the end, should we usually put this? So I know that seems strange, right? But you want to end up putting units on your final answer just to get in that habit.
So remember, if in doubt, if the plot has units, even if I specify them in that weird way where I tell you the units in the problem statement, your answers had better have units on test day, right? I don't want you to lose half a point here, half a point there for not writing the units, because that starts to add up. So if you're writing a number and you can figure out the units, you better have the units on your answer. All right. Doing all right?
Kind of, I just.
Making some notes to yourself.
Yes.
Okay, gotcha. How are you doing?
He's just right.
Oh, okay. You want an extra book? For a sec, just make sure I get it back, all right? Got it? I'll save you some time. Everything, getting it done?
Yeah, like on view. Because you said X is a term, so it's going to be good.
Yeah.
So then, the derivative will be 1 over nanometers.
So EV, EV over nanometers? So then you're gonna have to convert, or you could leave it as EV per nanometers.
Well, I was converting it to the joules,
Exactly, you convert the EVs to joules.
and then Newton meters.
Yeah.
Newton over.
And then you could change the nanometers to meters. Which part is this one? Yeah. By the way, everybody, class, one of the things I usually do with this problem is I require you to answer your forces in newtons. So I force you to do the conversions just to see if you could do that. I'm not trying to hide anything here. It's just, I like my forces in newtons, not EVs per nanometer. Just be aware. Okay, got that? So practice that unit conversion as well. In part D, I think I talk about that. So maybe put a star next to part D so you know how to do that conversion on test day. Yeah.
Oh, that's what it asked.
I think so. Aren't you supposed to figure out the units?
No, it doesn't.
Oh, well, it says what are the units of this force, right?
Right.
What are the units on your plot?
It would be EV
Per,
per.
right, and then you can convert those to newtons if you have to. Figure out the conversion factor. Got it? So that's what I'm saying. And you'll see this actually on the next one. One of these days, somewhere in here, you'll see it on the next one. I'm gonna practice this.
Yeah, then I cover.
Basically, realize that if I give it to you, you can answer it, then I have to do the first. All right. You don't need to do the conversion.
How much is an electron volt? Yeah, it's probably 1.602.
Right? More than half that. Yeah. Yeah, just set up this conversion. Yeah. But then obviously we're not going to take the time to do everything. Well, it's just, yeah, exactly. When you do the practice test, you'll see. Keep on things for so that's kind of like heads up, watch out. So those are- Okay, cool. Oh, get the plots, the points. Yeah. So that we want the equilibrium points. By the way, I would put nanometers on there, so you know those points, right?
Right now, it's 9.
Federal degree units in this case.
What is that in terms of?
Right, okay, then wait, what was your question now? Yes, so for B, we want points. That's these.
9.
Oh, wait, oh, I switched the order. Oh, sure. No, okay, so determine, oh, I see what I did. What I did is, you agree, I just looked at the graph. Right, and then here's the answer for the force, and then this is all a side note. By the way, if you want to do a better job, there it is. Yeah, so. Right. So you could get the equilibrium points by just reading them off the graph, and that would be good enough.
Basically, you're just
Next, if you needed more sig figs, you do this one. That, yeah, sorry, that wasn't very clear. That whole thing was the side note. That's good. All right. Yeah, for it.
9 times that.
Good.
The units and the force. It's embedded within our equilibrium.
Correct,
Yeah,
correct.
perfect.
So what units are you going to get?
One units of the force equation. What are units of this?
Joules.
No.
EV or nanometer.
Yeah, so your force is in units of EV per nanometer. Which is a horrible set of units, but it is a legit set of units. Good? Cool. Yeah, yeah, yeah. I'm just trying to point out that now we're taking it to the next step, we're taking into detail of what the units mean. So if you flip the units, figure it out. Sorry, that's kind of goofy way to phrase the question.
Is there a way to like convert? Better way.
You could do that, sure, you could just take your.
That's what the experts say.
Except you have, see, that's terrible, what are the units apply on this number? Your constants all have units too, right?
You have to change it.
Exactly, and so that's the thing, is people don't think about the units associated with these constants. Now, I did imply that, and so that's why I'm always like, always understand your units before you start messing with them. Got it?
Yeah.
And the easier way to do it is do it all in Excel and then make a table and then just convert the tables because you can use the conversion factor on the final products. See what I'm saying with that?
Yeah.
And so in part D, you're figuring out that conversion factor to make this a normal. Is it go per nanometer or? Figure out how to get that in.
You have to like
Yeah, write it down. Make it know. Okay, gotcha, gotcha. Cool. And you can sketch it right here if you want to draw the dots. You can see the picture. Get there? Kind of.
Different one.
Okay, yeah, sure, whatever works, right? Okay, okay. Should I go away or?
yeah, I just
I just get it.
Yeah. What do you think? Get somewhere? Sure. Should we leave for a second or anything like that? Any questions or?
Yeah, because every time you go to the problem, you're using something from before. So.
Yeah, exactly. I don't know, I try to do that just so that like every time you're doing something, you have to remember something else and eventually, right? If you do something 30 times, it sticks. If you only do it once or twice, it doesn't. Yeah. All right, I'll let you read. What do you think? You just talked to Dom, so you're good for that. All right. What do you think? Want to sketch that plot? Yeah.
I want to get into kilograms times meters results.
What's a joule?
Kilograms times meters squared.
I like the way you wrote that out there, because then you could see it easily, right? You would have caught that. Oh, how you doing, Jules? Good? Yeah. Whatever. It's fine. Watching the live stream later, right? So you're good on that?
Yeah.
How about you? Yeah, okay.
Breath is, what is the needed visual speed required?
Oh, I love it. I love it. Okay, that one. I love it. I want you to see what you think. Start. Definitely not. All right.
that's
That's an electron.
no, yeah, that's the initial velocity.
Yeah. Probably let people struggle for a bit, then I'll end with card like that. Swap. Okay. So you just put the dots in there and see, six to one, see, same like that. Obviously, in the real world, we use Excel, but just for this, it's good enough to kind of get a feeling. So you can multiply by two. Oh, yeah. So. Yep. So it's not weird, the fact that it's like 10 minus 10.
Yeah.
Yeah. Looks good, right? Good. And how would you convert to newtons if you had these numbers? Yeah, exactly. So just write out that conversion, just to make sure you practice it good. Okay, so good?
Yeah.
Right. Right. Yeah. EV per nanometer to newtons. Right. Yeah, write it out. Just railroad track it. You know what I mean by that?
Yeah.
Yeah, okay. Don't try to do it in your head, just railroad tracks. And then don't forget, a joule is a newton meter, right?
Okay, so that means I have to multiply by.
What is it, still good? Non-conservative.
Non-conservative.
So like friction. That's the chapter 7 stuff where we said work was equal to force dot displacement. We said force times the distance, and then we drew the picture of the two arrows. Got the angle between. Like. So basically, for the most part, it's not always true, but almost exclusively it's friction for this class, right? Because springs conserve energy, gravity conserves energy, friction, and I guess tension would be an external force.
Okay, is that the only time we take work non-conservative into account is with friction?
I would say work non-con or external. So it's usually tension from a zombie or friction. And then what do we do? Right? You draw a block.
Then at that point, it's just going to be the force dotted by the displacement.
Maybe there's a tension here and maybe there's friction. So then what could you do? You could say the work done by friction equals friction times distance times cosine of some angle. Say friction's this way. Distance is this way. Displacement, excuse me. In this case, the angle is 180. So remember we did all that? That's how you account for the work done.
Okay, I see.
Gotcha.
And then as for the potential energy, that's where we got the 1/2 K.
X squared.
Mhm.
Yes, yes.
Okay.
So the idea is anything that we can do the energy on, it's easier because then we don't have to do this every time. It's so much easier, right? So only the terms like friction, that's when we have to do this stuff. Otherwise, we go. And then I guess these should all be final. These should all be initial. Does that make sense?
And then potential energy is found from force doing the
Potential energy, yeah, we do the derivations, and then we stop doing the derivations and use the shortcuts.
Yeah.
And this one, I guess. So anything that we can use our shortcuts, geez, we want to use them. And on a lot of problems, if there's no friction, we don't have this term at all.
And what does the K stand for?
Kinetic energy. Kinetic moving V. Got it? That help?
Yeah.
Yeah. So if you want to try these problems are like here. And obviously here U initial is both spring and gravity because sometimes you have both, sometimes you only have one.
Mhm.
Cool. So if you want to look at one of these to kind of practice that while you're thinking about it,
We got 15 minutes if you want. Yeah. Questions?
So like work is delta.
If you include the work done by all forces, conservative and non-conservative, then work equals SBA. Or if you only include the work done by non-conservative, you might be wrong. Right? So in chapter 7, we said work net from all forces that exist. So we delta K. In chapter 8, we split it up where we use some of them as potential energy because it's faster. And then the only ones we have to do external is like friction or tension.
I was thinking like work equals delta K, delta K sign, work equals,
Yep, work equal one force is negative delta U if that force is conservative. Right?
I was seeing how that would relate to the equation like this. Now,
So I'm gonna rewrite this a different way. I'm gonna move all the initials to the other side. I'm running out of room. Can I get rid of this? You don't need this anymore, do you? I can erase this?
Yeah.
And you, I can erase that? Look, let's say I move all this crap to the other side. So I get work external and non-conservative is delta U for gravity plus delta U for the string plus delta K, right? Well, isn't this minus the work done by gravity? And isn't this minus the work done by the string? By the definition. Now I'll bring that over and I get work total, all forces, conserved and non-conserved, equals delta K. This was chapter 7. This was chapter 8.
This is like,
Either method works. However, this is a lot faster in practice. So we usually, even though it's adding complexity, because it's so much faster, it's worth it to learn that style. Is that good?
yeah,
Yeah. So remember the work. So for one conservative force equals negative delta U of that same conservative force versus work total from all is delta K. Subtle.
minimum speed.
Yeah. Now check this out. One more way to write this. What if the work was 0? If work equals 0,
This is a more-
you agree delta K
What's the minimum
Equals-
speed you need?
negative delta U? Just take a second. Move this to the other side, right? This is how some teachers introduce this. They say that changing your kinetic energy is opposite to changing your potential. That's what we were talking about. As you fall down, you lose potential energy. Well, negative of a loss is a positive. You gain kinetic. So when we're thinking about that marble shadow crap, yeah, I'll try it. You know what I'm saying? If you lose potential, that's a gain of kinetic. Good. So,
I'm just gonna much practice.
yeah. This probably was what you're reading too. Hopefully that helps you as well.
Slowly making.
There's lots of different ways to think about it, and the more ways you can understand it, usually the stronger your understanding. But of course, it's also time consuming.
Yeah.
Yes. All right, you good?
yeah, because I was using the word too. I didn't agree with the-
Yes.
I feel like that was all the way.
No, that's not the network. Okay, and now you know that trick, right?
Yeah.
Remember what I was kept saying? I was like, don't double count the work done by gravity and the potential. Either do U or work for gravity. You either do U or work for spring. Obviously, U has much more power because we use plots and understand much, it's got more versatility, even though it's more fundamental things. Is this work energy that you said. And that was the derivation. It was all lost. So those are good.
How much?
Yeah, looks like you got it, right? Nice.
Just get you.
Yeah, go. Didn't get on the grass at this point? Yeah. You gotta do a couple more, but you're at the point where you should be able to practice. Did you get that last part correct?
This is the total one.
Yeah, that's tricky, right? That's a classic thing. Yeah.
Small.
Put a star next to, what was that problem? 8.26F. Make sure you understand that, right? That's a classic exam question. Jules has had it on multiple exams, I think. Yeah, right, like what's the speed to get over the well? Remember that? I think I used it on the midterm and the final, 163. So, yeah. It's usually on one line.
Minimum can.
Oh, it's massive electron.
Or like Google and I still see those somewhere.
Oh, yeah. Sorry.
Get up here, you need speed, right? What's the, if your speed is zero, you can make it zero. So if you reach the zero speed anywhere here, you can make it.
Cool.
Thank you. I was just like, am I supposed
Yeah,
to,
yeah.
Google, am I supposed to know?
It's tricky, right? Because like on test day, I would give it to you, but then sometimes when you do homework, I leave that.
Yeah, I just wasn't sure. I was like, just-
Right. Yeah, sorry.
So I was like scanning the page.
Are we
down,
checking
like,
for
right.
test? Like, this one is more of a real world tech probably. to look up stuff.
Total energy is constant.
Oh, shoot, you need that? Don't?
No. Go ahead.
I can lower it?
Yeah.
Okay.
Come on now. You guys keep working while I get something on the screen here. Need to do this. So maybe, I know we've got about 8 minutes left. If you have a second, maybe we can all look up at the front. I don't like stopping you while you're working. You guys are doing awesome today. I hope you're learning some stuff. I just thought, we're gonna do practice tests on Thursday in lab. But let's just kind of look at what we're supposed to know here, and hopefully you can see this. This is the study guide, right? Kind of look at all the things that we've done. Newton's laws, in particular, what's the one that people tend to have trouble with? The third law, right? The action reaction. So it's on your test. And I'm looking to see if you screw up the action reaction. What's the most common screw up? People think that normal force and mg are an action reaction pair. Not true. Never true. All right. So we're going to do some FBDs with or without friction. Usually there's 2 blocks so that you could either do block 1, block 2, or in certain cases, you could also do a system FBD. You know what I'm saying? I'm going to say it like this.
Sometimes the system FED is very useful, sometimes it's worthless. So basically you kind of want to know it just in case it shows up on your test. It could save you a lot of time. Circular motion, you're getting it. It's going to be there. It'll be nasty. So, right, you got to know your circular motion force problems. There's usually some concept questions. We've got these two topics, and maybe I probably should have put these with it, right? The power and the work energy from chapter 7. Make sure you do a couple of those. I'm not going to try and lose you on that. Those ones are going to be very similar to whatever we did in class or in the workbook there. I hope you can remember that. You could go back and look at what we did in chapter 7. Here's what we did today. Determine U from F and F from U. And then this is what I was trying to blather on about. Sometimes when you use the 0, I mean, I'm not trying to mess with you, but every once in a while you'll get some situation where U initial should not be 0. These ones right here, these tricks right here, all of these right here, that's all for your energy problems. So here's the thing. If you practice the energy problems, you're going to be really fast at them, and this should be automatic points. But there's a number of tricks. Oh, do you have my book? Oh, yes. I just want to borrow that. I just want to point out, when you're studying for this, I think it was at the bottom of some page. There's a lot of those tricks at the bottom of page 19. Do you remember that? The tricks? That's kind of what I'm talking about right there. But one of the more common mistakes that I've seen over the years is this. Let me clear this out. The springs. Sometimes people really want to use force equals Kx. If a spring is not changing length in a problem, that's a great idea. But if a spring is changing length, usually you want to do it with energy. Why? As a spring changes length, the force changes. All right. Should we look at a couple of old tests and see if you recognize the problems for fun? I like to do that. You got 4 practice tests. Do them all, and you'll rock this thing. Okay? Don't do them all. Well, maybe not. Oh, gee. I wonder where that problem in the workbook came from, right? This looks like some Newton's second law, third law concept questions, right? There's that classic problem, and it's all or nothing. It's on pretty much every midterm and every year, and somehow people still screw it up. Blows my mind. All right. What type of problem? Take a second to read this one and tell me what kind of problem you think it should be. Give yourself a second. You got a block, level floor, light spring. It's going to slide and then come to rest. What type of problem? Is this going to be force, kinematics? What do you think? Is the spring changing length? Due energy. Remember that trick. It's not always going to work, but almost always. Do you agree the spring is changing length here? That's your clue. This is not a good one to do force because I have to do integrals. Do energy because the energy already did the integrals for you. Did that make sense? Is there work in this problem? Is there external work, non-conservative force? Is the spring a conservative force? Yes. So we're going to do energy for the spring. Is there any force in here that's not conservative? Friction. So you're going to have to do the chapter 7 technique of draw the force, do the normal force, get mu kinetic times the normal force. All right, let's keep going. Here's U of X. You've got a conservative force. You get this function for U of X. In this case, what are we trying to figure out here? Oh, we got some units. Determine the force. How do you do that? Negative derivative. If you forget, where do you look? Equation sheet. Good. All right. Equilibrium points. What do? You liking this test? You feeling like you can do this stuff? You gotta practice, but you can do this. What's that? Yeah, right. That's because we've been doing it all day. Oh, look at this 4D. This one's, let me make this a little bigger so you can read it in the back. All right. A particle starts at the origin to the left with speed v0. Determine the speed after it travels. How do we figure that out? This is tricky. This is something I haven't talked about a lot today, so I'm going to just show you. This problem is we could use U initial plus K initial equals U final plus K final. Now, in this problem, somewhere up in the problem statement above, it specifically said there's no other forces. That's why I'm able to do work equals 0. Now, look. K final. Whatever. Yeah. Sorry about that. But, right, if we know the initial speed, I'm looking for the final speed, so I'm looking for this term right here. That's what I'm looking for because the speed is in there. I could figure out U initial and U final from this equation. It starts at the origin, X initial is 0. In this particular problem, do you agree the initial energy is not 0? So that's what I was saying is in this equation, if you plug it in, the initial energy would be U0. Did that make sense? If you see a question with a potential energy graph and it's talking about speed, I want you to write that equation on your paper. And then basically you use the graph to get U initial and U final, or the equation to get U initial and U final. That's how these problems are different. Did that make any sense? That's the main difference. You're still using conservation of energy, only you're getting some numbers from the equation or the graph. We're almost there, sorry. All right. If you got to go, you can go. Let's get through this test. Oh, okay, blah, blah, blah. Oh, this is the question, which one's bigger? That's basically the one with the higher power matters more. Oh, look at this one. What type of problem is this? FPDs, force equations. There's friction. What force is holding up block M? There's got to be friction or it would slide down, right? When you see this word, minimum coefficient of friction. What's it? It's on the verge. So what equation might you write on your paper at that point if it's on the verge? F equals mu S times the normal force. All right. Keep going. Okay, blah, 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 blah. Oh, your favorite. This looks like what we just did today. You know it's coming. Look at the units, EV, nanometer. Okay, I think you could do this. Oh, that one's out of the book. Oh, that one's out of the book. Look at this. This is something I've been doing lately, it seems, where I'll put, some of them I'll actually give you numbers, right? And so if I give you numbers on a test question, usually you better have units on your answers, right? If it's algebraic, you don't need the units. Looks like a pretty straightforward question. Okay, blah, 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 blah. Oh, look at this one. I'm telling you that. So notice there's two circular motion force problems. This is pretty typical of me lately, where I'll do one horizontal circle and one vertical, not always, right? One where you kind of have to think about ATAN and one where you don't. This is basically ball on a string, except it's a normal force instead of tension. What was that problem with the ball on a string? You remember that one? I swear I'll shut up after this. I appreciate you guys sticking around for this. You can leave if you gotta go, but 6.52. Put a star next to that and redo it. We spent a long time, about an hour on that problem, right? You can learn a lot from that problem. 652. Page 114, if it helps, page 114. And you can see it's basically the same frickin' problem. I just pick a different angle. You do it. Okay. I mean, this looks. All right. Oh, yeah. All right. Get out of here if you want to go. Okay. If you want to look at more tests, we can do that Thursday, I think, right? I feel like you guys are going to be ready for this. If you just practice, you can rock this. 652, page 652, page 114, ball on a string, star on a string or something. All right. Thank you for putting that laptop away. If you guys could do that, that'd be great to get the laptops back. We start chapter 9 next time. Finally had a chance to do some practice problems today.